One of the lessons before, we talked about forces, and that forces can be equivalent to changes in momentum. And so we're going to use that concept to talk about thrust today. So a good example of this, of how rockets use thrust to move, is a cannon on a boat. So when a cannon shoots a cannonball, the cannonball moves in one direction and the boat moves in the other direction because the cannonball is the action and the boat is the reaction. So the cannonball moves in one direction, boat moves in the other. The equation of thrust is that thrust, which is a force, is the mass flow rate times the exhaust velocity. And we're going to go into what that really means. If we take the boat example and we shoot a cannonball out of it, all right, so the cannonball is a certain size and it's shot out with a certain velocity. But what we can do is we could lower the mass of the cannonball. So we take the cannonball and we make it much smaller and we shoot it out with a much faster speed. But it turns out that would have exactly the same momentum as a large cannonball moving with a slower speed. In rockets, we use exactly the same concept, except instead of cannonballs, we're actually using like little atoms and molecules, and we're shooting them out of the back at very, very high speeds. If we increase the rate of shooting cannonballs, so if we added another cannon and we shot a second cannonball, then the boat would move faster going in the opposite direction. So you add more cannons and the boat's reaction would be much larger. So let's talk about this in terms of thrust. Thrust is the mass flow rate times the exhaust velocity. In our cannonball example, thrust, so how much force we're applying to the boat, is equal to the rate at which we're shooting cannonballs off times the velocity of those cannonballs. So if we wanted to increase that thrust, we would shoot more cannonballs or we would shoot them at a faster velocity. And both of those things would increase our thrust. It turns out that the mass flow rate is easier to change. So to change the mass flow rate, as we talked about just a few seconds ago, all we have to do is add more cannons. Okay, so if you just keep adding more and more cannons, hopefully you don't sink the ship because you've added too many cannons, too much mass to it. But you add more cannons, you shoot off cannonballs at a faster rate. You don't have to change the velocity of those cannonballs at all. You just shoot more of them off, and then your ship then moves faster backwards. 3 times cannons equals 3 times the thrust. It's very easy to do that. But to change the exhaust velocity, so let's say you have a cannonball that's a given size, how could you shoot that off with more velocity? Well, so you'd have to develop something like a new gunpowder to do that, or you'd have to develop some sort of a new cannon that could take more gunpowder, something. You'd have to develop some sort of new thing, and that is science. So in order to change the exhaust velocity, the velocity of the cannonball coming out, that's where rocket science actually comes in. One of the big things that happens in rocket science is a work to try to increase the exhaust velocity. How can we shoot a cannonball faster? That is a lot of the effort that goes into rocket science. So what does this have to do with rockets? Well, so let's take the SpaceX Falcon 9. And, it is a certain size and it can take a certain amount of stuff to orbit. It has a certain thrust. If you wanted to take more stuff up to orbit, you want more thrust. So how do you do that? Well, instead of redesigning their engines so it has a larger exhaust velocity, what they do is they just add more engines to it. So a Falcon 9 has 9 engines. That's why it's a Falcon 9. The Falcon Heavy has 27 engines. So they just add 3 times as many engines. So that's 3 times as much thrust. So it can't really take 3 times as much to orbit, but it has 3 times as much thrust when it's sitting on the launch pad. So it's a bigger rocket. All they do is add more mass flow rate, more engines. But they don't fundamentally change the exhaust velocity or anything, because that's much harder to do. So let's talk about an example. Let's calculate how much mass flow rate it takes to hover a rocket. Let's say that you have a rocket that's sitting on the launch pad, okay? And all we want is that rocket to just hover there, all right? That's sort of not very realistic, because you would hope that that rocket would take off and go into space or something. But it's really easy to sort of calculate how much mass flow rate it would take to actually hover this thing. And so what you do is you set the force due to gravity equal to the thrust, and then you can calculate the mass flow rate. In order to do that, let's pretend that we have a rocket that is 10,000 kilograms or 10 metric tons. The acceleration due to gravity is 10 meters per second squared. And so the weight of that rocket is 100,000 kilograms times meters per second squared, which is newtons. So that means we want to set the mass flow rate times the exhaust velocity equal to 100,000 kilograms meters per second squared, or newtons. And so what we want to do is we don't know the mass flow rate or the exhaust velocity, but the exhaust velocity for rockets is usually around 3,000 meters per second. That's very standard. So let's just assume that. So then plugging that into our equation, we have the mass flow rate times 3,000 meters per second is equal to this 100,000. So then you divide the 100,000 divided by the 3,000, and you get 33 kilograms per second. So we need to use 33 kilograms per second to hover. So that's roughly 8 gallons of fuel used every second, roughly. And so if you shot out 33 kilograms per second at this 3,000 kilograms per, at 3,000 meters per second, you would basically have that rocket just sitting there hovering. Now, the interesting thing is that as it is sitting there, it's losing mass because it's spitting that mass out the back end. It's coming off of the rocket. That means that the rocket is getting lighter every second by 33 kilograms. Okay? And that means if you continue to thrust at this rate that we're talking about, that the rocket will sit there and hover for just a second, and then it will start to slowly accelerate upwards, because now the thrust is a little bit larger than the gravity. And as it's spitting more and more and more mass out, it's becoming lighter and lighter and lighter and lighter. So it accelerates faster and faster and faster. And you can see that with something like the Saturn V rocket. When it starts, it looks like it's just sort of sitting there. And then as it moves up, it moves faster and faster and faster. It accelerates faster and faster and faster because it's losing so much mass every second. So in summary, the thrust of a rocket is easy to calculate. It's the mass flow rate times the exhaust velocity. The exhaust velocity for a rocket is typically around 3,000 meters per second. The mass flow rate is straightforward to change. So if you want to increase the thrust, all you do is increase the amount of fuel going into the engine or increase the number of engines, and that increases the mass flow rate. So you just add more engines onto the rocket, and then that increases the thrust. The exhaust velocity is much harder to change, and that involves a lot of physics and a lot of chemistry, and that's where the rocket science actually comes in. And then as the rocket starts to take off, it becomes lighter and lighter and lighter as they lift off because it's losing mass. So their acceleration actually increases with the same thrust. So the force of those engines stays exactly the same, but because force is equal to mass times acceleration and the mass is going down, the acceleration goes up all of the time. So rockets accelerate faster and faster and faster as they go up into space. Thank you very much.